one more important class. Okay, here what they proved, the existence of matter waves and how the material particle showing as a wave or behaving as a wave, they have proved. Okay, so what they have done in this experiment, so up to now de Broglie hypothesis and derivation, that is theoretical. Okay, this German experiment is experimental evidence of matter waves. Okay, this is experimental, that is theoretical. Okay, now this is Davisson and Germer, this great scientist. Okay, they proved what they proved. Just they proved electrons incident some electrons on nickel plate. Okay, nickel plate, this is some nickel plate. Okay, they nickel some nickel plate is they incident some electrons and they observed some diffraction pattern. Okay, diffraction pattern or diffraction phenomena. Okay, so if electron is showing some diffraction pattern, means what? It is behaving as a wave, right? Diffraction phenomena mainly due to wave nature only. Waves only we will get the diffraction pattern, right? Suppose if you have any small slit, if you send small wave, you will get the spreading of this light, right, about the edges. This is the diffraction pattern. Okay, so this diffraction pattern mainly due to waves only. Okay, now we will see how they have proved this experiment using this experiment. Okay, just very simple experiment. Just I will draw the diagram. From this diagram you can explain easily. Okay, you can explain what is happening and how they proved. Okay, just listen carefully. Just you will get very easy only, but important, very important. This de Broglie and Davisson German is very important. This will definitely come in the exam. Okay, this comes in the exam. Okay. First, what they have done? First, they have taken one filament. Okay, they have taken one filament, and here they have applied some low tension battery, and here they have applied some high tension battery. Okay, the high tension battery. Okay, high tension battery means some potential only. Okay, here we are applying some battery, means this is only. Okay, battery, you know, right? We are using this battery, we will apply some voltage, that's it. Low tension means low power battery, high tension means high power battery, that's it. Okay, using this one low tension high tension battery, they will heat and this filament. From this filament electron will eject. Okay, electron will eject. Here we will keep two slits, two collimated rays. Okay, to get the D1 D2 are two slits. Okay, two small very fine holes. Okay, using this split, we will collimate these electrons, or we will focus the electrons in a very fine focused beam. Okay, so from there we will get the electron. Okay, we will get the electron. Okay, that is the what we are calling this one electron gun. What we are calling this setup? Okay, this one we are calling this setup. We are calling a electron gun. You can say electron gun because it is emitting electrons, right? It is emitting electron. That's why electron gun will say. Okay, after that we will keep a here some nickel plate here. Okay, nickel material, nickel. Suppose nickel, any nickel crystal, or you can say nickel crystal. We'll write crystal. Okay, nickel crystal, and this crystal you can rotate using some handle. This handle means you can rotate the crystal any direction, you can move it. Okay, you can move any direction. Okay, after hitting these electrons here on the nickel crystal, this will some of the rays will reflect or some of the scatter and some of the diffracted. Okay, using this way this will direct reflect or diffract or scatter. Okay, we will see that one. Okay, after that here we have a scale. What is the scale? A circular scale, this one. Okay, this is, it measures 20 degrees to 90 degrees. Okay, this is some circular scale. Okay, you can why we are taking circular scale? Because this light ray reflect in this direction or maybe in this direction, we don't know, right? So for that you can fix a circular scale so that we can collect the electrons or we can collect the current from different angles. Okay, here you have a one Faraday cylinder. Okay, here double walled Faraday cylinder. What is this one? Double walled Faraday cylinder. Okay, here two walls are there. This is what we say Faraday cylinder. Okay, cylinder. Okay, Faraday cylinder, and this cylinder is connected to some galvanometer. Okay, what is the use of galvanometer? What is the use? Hello? What is the use of galvanometer? We can measure the current, just that's it. Okay. Are you listening, right?
Yes,
Yes,
sir.
sir.
Okay. So
Yes,
here
sir.
the okay, good. Thank you. Okay, see here first the experimental setup is like this. Okay, first they have taken one filament, that is tungsten filament or some high temperature. What material? Some tungsten or tantalum. They will sustain for high temperature. That's why they will take high temperature filament and they will connect it to one is low tension battery, one is high tension battery. Low tension means you can apply low voltage here. You can here high tension means you can apply high voltage here. Okay, once you give low tension voltage, low tension using low tension voltage, low tension battery, you can apply some voltage. From there electron will eject this from this filament. Okay, this filament pass to these diaphragms. What is this D1 D2 diaphragms? Diaphragm means nothing but slits only. Okay, slits. To passing these slits we are focusing this electron beam, very fine focus beam we are creating using these diaphragms. After that this electron beam falls on the nickel crystal. Okay, after this nickel crystal, some of the rays will scatter in different direction, or some of the reflect from the surface, some of the enter deep inside of the material. Okay, suppose material atomic planes are like this. Okay, so some of the ray reflected from the top surface and some of the electrons, high energy electrons, may enter inside the material, and this will also diffract. Okay, these rays will diffract whatever top surface reflect, and from the rays from the deep levels are diffracting. Okay, these are, you can say, diffraction. Okay, so these are diffracting and some of the rays are scattering. Okay, these rays will go in this direction. So we are using some circular scale. That scale we can measure 20 degree to 90 degree. Okay, this is the angle, some angle theta. Okay, incident beam and scattered beam, the angle is theta. Okay, using this theta you can vary. Okay, we don't know either electrons are coming this direction or some other direction, this direction we don't know. That's why we are using circular scale. On the circular scale we have a Faraday cylinder. Why we use Faraday cylinder? To collect the electrons. Okay, whatever electrons coming from the nickel plate or nickel material, nickel crystal, they will come to the Faraday cylinder. This Faraday cylinder connected to galvanometer. Here galvanometer measures the current. Okay, how much electrons came into the this cylinder. Okay, you can move this Faraday cylinder to and fro, different angle you can move it, and you can collect the electrons. Okay, you can collect the current. Okay, that is the experimental setup. Suppose this nickel crystal also your handle is there, you can rotate this crystal. Okay, depends on your requirement, you can rotate which angle you want. Okay, which you want a nickel crystal this way, or you want this perpendicular, or you can it slanted, you want how much how you want, you can rotate using handle. Okay, this is the experimental setup. Okay, is this clear now? So this Faraday cylinder also, this Faraday cylinder always we are giving negative potential. Why we are giving negative potential? Because so here from the electron, so nickel crystal means what? Nickel crystal means what? What is the crystal? Anybody? Crystal? What is the crystal?
Solid form, sir.
Solid
Yeah,
form.
Atom
solid.
systematic.
Yeah, good. That is good. Okay. Solid amorphous materials also available in solid form, but crystal means crystal. Suppose you have any crystal, nickel crystal or some any other crystal, NaCl crystal. Okay, NaCl crystal. Crystal means atoms are arranged in a systematic manner. Okay, periodic manner. Okay, systematically and periodically. Okay, that is the crystal means. Okay, amorphous means what? Amorphous means atoms are arranged randomly. Okay, there is no order. Okay, the zigzag. Okay, they will arrange very randomly. Okay, this is nickel crystal. Suppose the from these electrons are coming, right? High energy electrons are coming. From there it will reflect. Some of the electrons will reflect. Some of the enter into this layer. Enter into this, what we call this one, atomic layers. What is this? Atomic layers. Okay, atomic layers. Okay. Here the spacing between these two atoms we are calling d spacing or atomic spacing. This d spacing is same anywhere in crystal. If you take d here same, here also same, here also same, because atoms are arranged very systematic periodic manner. So there is no deviation of atoms in a crystal. So here, suppose here it is hit the this one. After that it will diffract. This will reflect back or diffract. What we will carrying diffract. Okay. So once this electron hit here, here also electron eject, right? Is it possible? There is a chance of ejecting the electrons from nickel crystal also, because we are incidenting some high energy electrons on nickel crystal. Because of this high energy electron, there is a chance or there is a possibility of ejecting electrons from the nickel crystal. So these electrons we are calling secondary electrons. What is that? Secondary electrons. So what is mean by secondary electrons? Suppose you are incidenting some high energy electrons on nickel crystal. These high energy electrons ejecting another electron from nickel crystal, that is secondary electron. Okay, so we want only collect the electron whatever coming incident, this whatever electron ejected from the gun only, we want to collect these electron only, not from nickel crystal. That's why we are always applying negative potential, so that we can only collect the electrons from which are ejected from gun only. Okay, that means fast moving and high energy electrons only reaching Faraday cylinder here. Okay, that means we are not collecting electrons from nickel crystal, which are secondary electrons. We are not collecting secondary electrons, only fast moving electrons from electron gun only we are collecting using Faraday cylinder. That's why we are up. Sorry, just a minute. Note, note is gone. I don't know. So is this clear? Why we are taking? Why we are applying this one negative potential to the Faraday cylinder? No. Hello. 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 Are you listening?
Yes, sir. Yes, sir.
See, here secondary electron means, suppose I will explain again. So using Faraday cylinder, in this cylinder, in this Faraday cylinder, we are only collecting fast moving electrons and primary electrons from electron gun, because secondary electron means we are using some electrons from the gun, here gun. Okay, these are incidenting some nickel plate. Okay, this is some nickel plate. Okay, nickel material or nickel crystal, whatever. Okay, when this electron hit this nickel, here also some electrons will eject, right? Oh, what happened? Why it is just a second, please. Why it is one note is sharing is going up? I don't know. So you can see, right, PPT, these notes. I don't know, some because of some technical, that is screen is sharing off. So sorry for that. Okay. So here we are ejecting electrons from the filament. Okay. These electrons also eject some electrons in the nickel, right? Once this hit the nickel plate, here also some electron eject. These electrons we are calling secondary electrons. Secondary electrons. So we don't want to collect these electrons. We want to only collect these electrons. That's why this Faraday cylinder, this double wall cylinder, we are applying some negative potential or retarded potential. Okay, so that only we are collecting only fast moving primary electrons only. Then only we can see these electrons are diffracting or not. We can see, we don't want these electrons. We don't want electrons from nickel. We want only electrons from electron gun which are diffracting in nickel crystal. Okay, this is nickel crystal planes. Okay, nickel crystal planes. Okay, this just I will draw again. Please wait. I don't know whether you are following it or not. So this is the nickel plate. Okay, this is the nickel crystal, means here I am drawing a lines. Okay, lines. Okay, here atoms are arranged in a systematic manner. Okay, you can see this one. Okay, here electrons are coming. Okay, electrons are coming from electron gun. Okay, and some of the reflected back, and some of the electron enter into deep levels, and here also diffracted. Okay, once this electron hit here, here also some electron eject, right, from nickel. These electrons ejecting from nickel, but we don't want to collect this one. We want to see whatever ejected electron, these electron, whether these are diffracting or not. We want to test these electrons, not these electrons. We are testing electron from the gun. We are not testing electrons from nickel crystal. That's why we want only electrons from nickel crystal. Whether what is happening today? So just a second. So we want to see electrons ejected from the electron gun diffracting or not. So we don't want electrons from nickel crystal. That's why we are collecting only primary electrons. Okay. After that, we'll collect the these electrons, and we'll plot the graph. We'll plot the graph. We'll see that graphs how we will plot. Okay. Just I am taking this another page. Okay. You can see now we are using galvanometer. We are collecting current, right? Isn't it?
Yes, sir. Yes, sir.
We are using galvanometer. Finally, electrons are electrons are incidenting on nickel plate, and some of the scattering, some of the diffracting, right? After this one, we are collecting that electrons, and we are measuring. Okay, we are measuring or we are plotting. Okay, just we take this one graph. Okay, here angle, scattering angle, here intensity, current intensity. You can measure the current intensity, or you can write current intensity. Okay, current intensity at different voltage. Okay, in the previous graph, in the just I will go to the previous this one. Just a second, please. So in this graph, you can see here low tension and high tension battery. We are applying some voltage, right? First we have applied 40 volts, after that 50 volts, after that 60 volts. So if you increase the voltage, these electrons also getting more energy, right? More energy, current, more electrons also emit from this filament, right? Isn't it? So
Yes,
here
sir.
you are applying more voltage using this battery, low tension battery and high tension battery. If you increase the voltage, more number of electrons eject from this filament. Okay, that means more number of electrons reach the nickel crystal, and after that, after nickel crystal incidenting on nickel crystal, this electron diffract in different direction. More number of electrons will diffract, right? Okay, depend on this voltage, you change the voltage and current is changing, right? Isn't it? So we are increasing the voltage at the filament. So more number of electrons are increasing and more number of electrons reaching Faraday cylinder, right? Isn't it? So voltage we are increasing. Okay, more number of our electrons are ejecting. So more current we are getting at Faraday cylinder, at galvanometer, isn't it? Is this clear, everyone?
Yes, sir.
So now we will plot the graphs. Okay, we will plot the graphs and we will understood what is happening. Okay, now we are increasing the voltage and electrons are ejecting, more number of electrons ejecting more, and after that this more number of electrons reaching nickel crystal, After that, reflecting or scattering or diffracting more number of electrons. If you increase voltage, more number of electrons eject and more number of electrons reach the Faraday cylinder. That means we are using galvanometer measuring more current from the this nickel crystal, because you got it right point. So you plot this graph at 40 voltage. We will plot the graph. Okay. And listen, fourth hour also I will take, because Amit sir is on leave today. So shall we continue in fourth hour, remaining part?
Yes, sir.
Yes, sir.
Okay, fourth hour also mine only I will take. Okay, we'll complete only small portion is there, that is very important.